Honors Chem, this is the answers video for lesson 13 on empirical formula. So we're going to learn what an empirical formula is, why it's used, and we're going to work some problems. The problems are about 6 or 7 steps. It's just a matter of practicing them. You'll find the steps are all the same in all of the problems, and so just the repetition will eventually get you there. Don't get frustrated at the beginning if they seem complicated. Just try to learn one step at a time, or one step each problem. Alright, so what is a molecular formula? Molecular formula, I'm just going to say this in words because I want you to put it in your words. It's the actual formula of a chemical compound. So for example, I'll just give you an example here. C2H4 is the chemical formula for a compound, a hydrocarbon called ethylene. Alright, so that's an actual molecule. You can actually locate that, find that molecule in nature. What an empirical formula is it's simply reducing that. So this is a 2-to-1 ratio. You have twice as many hydrogen as carbon. So that's called a 2-to-1 ratio. If there were 6 hydrogen and 3 carbon, that would be a 2-to-1 ratio. If there were 10 hydrogen and 5 carbon, that would be a 2-to-1 ratio. It just means twice as many of these as these. What the empirical formula does is it actually reduces that number down like a fraction. So if there's 2 of these for every 1 of these, the empirical formula would be CH2. Now there's no molecule CH2. It doesn't exist in nature. It's just simply reducing this, that there's twice as many of these as these, so it just kind of like, as again, like reducing a fraction in math. So it's CH2 is the empirical formula. So the next question then is, well, why do we use the empirical formula? The empirical formula is an intermediate step. It's a middle step. When you're trying to know what the molecular formula is of an unknown substance, and the examples we'll be using in this class are hydrocarbons, CH compounds. But if you're trying to figure out the molecular formula, and what you do is you do an experiment in the lab where you break down a compound. In the case of a hydrocarbon, you break it down into carbon and hydrogen, or some substance that has that. You figure out how much of that substance you have in grams. You then use that to figure out, and we'll show you how to do that here, into an empirical formula. And then from the empirical formula, with one additional piece of information, you can come up with the actual molecular formula of the compound. So empirical formula is an intermediate step in finding out the actual molecular formula of an unknown compound. Alright, so what you're doing is determining what compound is that, what is its formula. Alright, so you put that in your own words. It's also in the instruction video, and you can do that. Okay, so let's go to work on calculating some of these. And again, it's going to seem like a lot of steps at first, but it's just a matter of practice, and you will get it. Okay. So, compute the empirical formula of the following compound. So, it's some subscript of H, some subscript of O. So, we don't know what that number is or what that number is. But what we know is in a decomposition reaction, it produces 0.857 grams of hydrogen and 6.86 grams of oxygen. What is the empirical formula? So what you have to do is, I tell you in this assignment what the steps are. I walk you through it step by step. So just once you see an example, then hopefully the later ones you'll read that and you'll know what it's talking about. So write the molar mass of H and O. So the molar mass of H is 1 mole. And from the periodic table, it's right there. You just get it right off the periodic table. Okay, it's 1.01 grams of H. For oxygen, it's the same thing. You do it the same way, I should say. 1 mole of oxygen equals, periodic table says it's 16. It's not O2, it's just asking for oxygen, O. Alright, so there they are. Those are the molar masses. So as you know, you can always make 2 ratios out of this. You can put this one over this one, or this one over this one. So that's what we're going to do in just a minute. So now, whenever you're dealing with a compound formula or a chemical equation, you've got to be in moles. Chemical equations don't care how much the substances weigh. They care nothing about weight. They care about how many moles of hydrogen and how many moles of oxygen. It's numbers of molecules, numbers of moles that they care about. So we're going to do a conversion we've done in the previous assignment quite a few times. So we're going to start with the hydrogen. Grams of hydrogen. Okay, there's our conversion right there. So again, you want one of these on top and one of these on the bottom so that you end up with moles, because it's asking you for moles of hydrogen. So which one of these goes on top, which one goes on bottom? If you want to draw the box like we did in the previous assignment, you can do that. Okay, so you need grams of hydrogen to cancel out, so that has to go on the bottom. That means the moles has to go on the top. Cancel grams of hydrogen with grams of hydrogen and do the calculation. And we get 0.849 moles of hydrogen. All right, do the same for oxygen. And that gives us 0.429 moles of oxygen. Okay, so now we know how many moles of hydrogen and moles to oxygen. So what we're trying to do for an empirical formula is just find a ratio of how many oxygens for each hydrogen, or it could be the other way around, how many hydrogens for each oxygen. So for hydrogen, we have this number, and for oxygen, we have this number of moles. Now, some of you might be able to look at this and see what that ratio is, but I don't assume that you can do that. So here's how you do it. It says you create a ratio of the number of moles for each element you obtained. Place the smallest number of moles on the bottom of both ratios. So if we look at these two, the oxygen number of moles, the 0.429, is the smallest of these two numbers. So let's go ahead and do that. So for hydrogen, and I won't write the units here because we're just looking for a ratio, so units are going to cancel out. So if you do that on a calculator, what you will get is $1.98. Now, these subscripts, go back a little bit here, these subscripts have to be whole numbers. They can't be decimal numbers. So we're trying to look for whole numbers. 1.98 is close enough to 2 that we can say it's approximately equal to 2. Now, how close is close enough? I would say 1.95 to 2.05, 2.05 would be close enough to 2 that you can round it to 2. So we're going to say that ratio is approximately 2. Now we'll do the same thing for oxygen. Now, in this case, you're going to just put the number over itself. This is the smallest number of moles. And that's always going to be the case. The smallest number of moles is always going to be over itself, and so that obviously equals 1. So for oxygen, we have 1 mole compared to 2 moles. In other words, there's twice as many moles of hydrogen as of oxygen. So let's go to the next page and finish up the problem. Okay, it says divide the number of moles of H and O by the lowest number. So I actually just did that, all right? So let me just do it again in the right place. So it had just asked me on that previous part to just put the ratio, just set it up as a ratio. Let's just go ahead and do it here on this page. And we said that's approximately equal to 2, and that's for hydrogen. And then for oxygen, okay, so there we did it, what we did on the previous page. Multiply the top and bottom of the, by the way, what you should do is, when you reduce this, and it's unusual to do this, usually you just leave it as 2, we're going to put 2 over 1. Okay, we're saying that there's twice as many of these as these, so we want it to be a ratio. And this one is going to be 1/1. Okay, so we want to leave it as a ratio. I know it seems a little unusual when you do a division that you would do that, but we're going to do that here. Okay, so now it says multiply the top and bottom of each fraction. That's what it's talking about there. By whole numbers, 2, 3, 4, and so on, until you have a whole number on the top and the bottom. Note, the number on the top might be very close to a whole number, but not exactly a whole number. Well, we saw that already. The 1.98 we converted to a 2. Well, here's the deal. We already have a whole number here, and we already have a whole number here and here. So this part, we don't need to do that. You'll see on a later example where we do need to do that, and you'll see what it's talking about. So don't worry about this step right now. So now it says place these numbers as subscripts of the elements. This is the empirical formula. So I have 2 hydrogens for every 1 oxygen. I have twice as much hydrogen as I have moles of oxygen. So that's H2O. And that's the answer. That's the empirical formula. So the substance is, we now know, we recognize that as water. Now that's the empirical formula. We may not know, if we weren't so familiar with water, we might not know if that the actual molecular formula. It is. There's actually a molecule called H2O, which is water. But we might not know that. So we'll see examples coming up soon where we might not know if that's only the empirical formula or if it's actually the formula of the molecule. In this case, it's both. Okay, let's just do another example. The idea is just keep doing examples. But now that you've seen it done once, see how many of those steps you can remember. Even go back and do it on your own rather than just watch me do it. That's how you learn, is see if you can retain them and apply them each step. Okay, so now we're going to go down, something down here. It's an NO compound. So we're trying to find the subscripts here. And what we're given is in the lab, we were able to determine that we have 24.5 grams of nitrogen and 70.0 grams of oxygen. Again, we don't care how they got this. There are lab techniques to do it. That's not what we're dealing with right now. Just understand that in a laboratory there is a way to determine that and to weigh it. We're just interested in how do we get the empirical formula here. Okay, so write the molar mass of nitrogen and oxygen. So oxygen we know is 16 and nitrogen is 14.01. So the molar mass for nitrogen. Okay, there you go. There's the molar masses. Those are the conversions that we're going to need to do. So compute the number of moles of N. So we start with nitrogen. Grams, nitrogen cancels and cancels. So we divide 24.5. Well, we multiply 24.5 times 1 divided by 14.01. That gives us 1.748. I'm going to round that to 1.75. And that's moles of nitrogen. Now do the same thing with oxygen. 70 times 1 divided by 16. That gives us this. Okay, so we have this many moles of oxygen, this many moles of nitrogen. So what we're trying to find is a whole number ratio that's a relationship between those two numbers. So we come down below here. It says create a ratio of the number of moles of each element you obtained. So for nitrogen, for oxygen, again, the smaller number is always going to just be over itself. You just take the smaller of the two and put it under this and then put it under that. Okay? Now we'll go to the next page and do that calculation. That gives us 2.5. And that's for nitrogen. For oxygen, of course, it's just going to be 1. So we have a ratio where we have 2.5 moles of nitrogen for every 1 mole of oxygen. Okay, and again, we want to make a ratio out of that. So, really, I'm sorry, what we want to do is make a ratio out of this and this. When I said that, I kind of said that wrong. So it's 2.5. It's okay. That's for nitrogen on the top and 1 for oxygen on the bottom. So you really didn't need to draw that in this one or the last problem. So that's the relationship. There's 2.5 times as many moles of nitrogen as oxygen. Okay, but so that means your subscript, let me just show you what that would mean. That means your subscript, if you were to write it like that, would be N 2.501. But we can't have a subscript that's a decimal number. It's got to be a whole number. So that's where this step comes in. Multiply top and bottom of the fraction, the whole number, by 2, 3, 4, until you get 2 whole numbers. So let's start with 2. We're going to multiply this by 2. And you got to multiply this by 2. Even though it's already a whole number, if you're going to multiply this one by 2, you have to do this one by 2 also, to keep them in the same relation, that 2.5 to 1 relationship. So this is going to equal 5, and this is going to equal 2. Okay, and we don't have to go any further with the 3, 4, and so forth. That's a 5 to 2 relationship. Okay. So what it's saying is the formula is going to be, it's going to be N 5O2. So there's 5 moles of nitrogen for every 2 moles of oxygen, or, well, that's it. That's the empirical formula. Again, that may or may not be an actual molecule, N5O2, but it is the empirical formula. It's the lowest ratio of nitrogen to oxygen. And so that's your answer. Okay? All right, let's keep going. Okay, now you have some sort of a CHO compound. So it has 3 elements. It doesn't mean that the problem is done any differently. You just have an additional element to deal with, okay? So here are the masses: 60 grams of carbon, 4.48 grams of hydrogen, and 35.52 grams of oxygen. So let's write the molar masses. So for carbon, you get this off the periodic table. And we've already done that. It's 12.01. For hydrogen, and for oxygen. All right, now we got to figure out how many moles we have of carbon, of hydrogen, and oxygen using these molar mass conversions. So let's start with carbon. I'll start way over here so I have space. And that gives us 4.995, which is going to round, and we would have rounded it anyway if it didn't. It's going to round to approximately 5. We're just going to call that 5, okay? So that gives us 5. 60 times 1 divided by 12.01. Okay, let's do hydrogen. 4.48 times 1 divided by 1.01. And that gives us 4.435. I'm going to write that down here to save some space. I'm going to call it 4.44. I'm going to round it there. Okay, so that's this one's 5 moles. I should write the unit of measure, moles of carbon. This one is moles of hydrogen. Okay, and we'll try to squeeze oxygen in over here. 35.52 times 1 divided by 16. And that gives us 2.22 moles of oxygen. Okay, so here are the numbers we're interested in. The 5, 4.44, and 2.22. So create a ratio of the numbers of moles. So let's go ahead and do that. So for carbon, it's going to be 5 over the smallest of these 3 numbers is the 2.22. Here's hydrogen. And then oxygen's the smallest number, so it's just this. Okay, so let's go to the next page and we'll rewrite this. So it says divide the number of moles of CHO by the lowest number. Okay, so let's do that. We started to do that there. 5 divided by, and that is going to equal 2.25. Okay, you can't round that to 2. It's not, if that's not close enough to 2 to round it to 2. It has to be much closer to 2 than that. Okay, so that's for carbon. For hydrogen, it's 4.44 over 2.22, and I think most of you can see that's going to be exactly 2. That's exactly twice that. Okay. Finally, for oxygen, and that's simply 2.22 over itself, which equals 1. Okay, so these are the numbers that we're going to set up. So if we were to go ahead and write this, I'll just write it over here. Using this subscript, it would be C2.25 H2O1. Okay, but you can't have a subscript that's a decimal. So these two are already whole numbers. So if we multiply them by 2, 3, 4, they're going to come out to be some whole number. So we're not really focused on those. Let's figure out what we have to multiply this by to get it to be a whole number. So let's start 2.25 times 2. That equals 4.5. Well, that didn't do it. That's not a whole number. Let's try 2.25 times 3. That's going to equal 6.75. Well, that's not a whole number. Let's go to the next one. 2.25 times 4 equals 9. That does it. That's a whole number, so that's good. But what that means is we have to multiply the hydrogen, the 2 for the hydrogen and the 1 for the oxygen, these numbers, also by 4. Okay, you can't just do one of them. You have to do all of them. So if we multiply 2.25, what we get down here is our final answer, which is C9. And then H2, but you got to multiply that by 4 as well. So that's H8. And then the O1, you've got to multiply that by 4, so that's O4. So that's the empirical formula for that particular problem. Okay, again, that might be an actual molecular formula of a real-world molecule, or it might just be an empirical formula for something else that's bigger than that. Okay, all right. Now we're going to get into a little more complicated problem. We're going to be dealing with a combustion reaction. That's where you take a hydrocarbon, CH compound, you mix it with oxygen. So this could come out of the outlets inside the chemistry classroom. Mix it with oxygen in the air, then you have to light a match to it. So combustion means it's burning, and that'll produce carbon dioxide and water. This could be any number of hydrocarbons. There's lots and lots of hydrocarbons. But it's always mixing it with oxygen to produce carbon dioxide and water, and that's called a combustion reaction. Okay? What these boxes are is similar to the boxes. They're not identical to what we used boxes for before, but they're basically something for you to fill in to see how the problem is proceeding. If you look at the instruction video, which you should, watch that first please, then you'll kind of see what we're doing here. Okay, so empirical formula. Determine the empirical formula for the hydrocarbon. So we're trying to figure out what those question marks are. C something, H something. We need to figure that out. Okay, so follow the logic. Don't feel frustrated if you don't get it the first time. Just try to learn one new step each time you do the problem, okay? All right. Okay, so here's what's happened. You've done this reaction. You don't know what this is, what that chemical formula is. All you know is you burned it with oxygen, and using laboratory processes that chemists can use, you figured out how many grams of CO2 you had and how many grams of water came out of that reaction. Okay? That's all you know. You know how many grams of each of these products came out of that reaction. And from that, you're trying to figure out what the formula for that compound is. Okay, so how do we do that? Well, first, let's just follow this. It says write the number of grams of CO2 and H2O in the appropriate boxes. So that's right here where it says grams of CO2 or H2O. So for CO2, it's 5.72 grams. And for oxygen, it's 1.17 grams. This is exactly the same problem as in the instruction video with the same numbers, but try to do it on your own. Okay, you saw it in the instruction video, now try to do this on your own. Okay, so check, we did that. Okay, you don't need to do anything there, you did that. Okay, next step. It says, compute the molar mass of CO2 and H2O. Okay, so that's similar to what we did on the first 3 problems of this assignment. So come down here. Okay, except this time it's a compound, it's not just hydrogen and oxygen. So how did we do that? So we said carbon, there's 1 carbon. The molar mass of carbon is 12.01. Okay, and there's 2 oxygen, 2 of those, and the molar mass of each oxygen is 16. Get that, you add those together, you get 44.01 grams for CO2. Okay, next H2O. So write this up here. Okay, so hydrogen, there's 2 of those. Times 1.01 and oxygen, there's 1 oxygen times 16. You add those and you get 18.02 grams for oxygen. Excuse me, for water, H2O, sorry about that. Okay, there you go. All right, so there's your molar masses right there. So now using the mass of CO2 and H2O, compute the number of moles. So this is exactly what we did in the first 3 problems. So we're going to come down here, and we have 5.72 grams of CO2. And there's the molar mass. We need grams of CO2 to cancel out. Grams CO2 cancels with that. So 5.72 times 1 divided by 44.01 is going to tell us how many moles of CO2 we got out of this chemical reaction. And that turns out to be 0.1299, which I'm going to call 0.13. Alright, let's do the same thing for water. So we had 1 point up there above where you can see right now it's 1.17 grams of water. Grams H2O cancels there and there. 1.17 times 1 divided by 18.02. And that gives us 0.0649, which we're going to round to 0.065. Okay, we'll call that 0.65. So that's how many moles you have of water. Okay, so now we're going to come back up here and fill in our boxes. We just made this conversion from grams of CO2 to moles of CO2, which is 1.13 moles. That's what this row is asking you to do. And for water, we did the same thing. For water, for H2O, it's 0.065 moles of water. Okay, now, let me put that back on screen right there. So now we're sitting in those two boxes up there. Now we go to the next page and it says, okay, so this is the part I want you to really master and knock down. Writing a two conversions equation, compute the number of moles of carbon from grams of CO2 and place in the appropriate boxes. So let's first of all understand what's going on here, okay? You know you have this many moles of CO2. You don't care about CO2. You really care about the carbon. Why? Because if we can figure out how many moles of carbon, look at this equation. We know that the only place we have carbon on the right is right there. So all the carbon that was produced in this reaction is sitting right there inside the CO2. And where did all of that carbon come from? The only place on the left that we have carbon is right here. So however many moles of carbon we end up in this compound, CO2, that's how many moles of carbon we had to start with. Remember, mole is just a number of atoms of carbon. It's just some big number of atoms. You can't create or destroy atoms of carbon. Whatever number, if you had 2 here, you have to have 2 here. If you had 327, I'm just making up a crazy number here, you have to have 327 here. All the carbon from here, the carbon only came from here and only went to here. So whatever amount of carbon you have here is the amount you had to start off with here. So how do we figure that out? Well, you just look at the chemical formula here. For every one CO2 molecule, I'll write the numbers even though we normally don't write a 1 out in front like that, you have a subscript of 1 here. When you don't see a subscript, it means it's 1. You have 1 carbon atom for every 1 CO2 molecule. So it's a 1-to-1 relationship. So if we have 0.13 moles of CO2, this is moles of CO2, that means we must also have 0.13 moles of carbon. And I should be writing that this is CO2 and that this is carbon. I'll just write it up there. This is for carbon. This is for CO2. This is for carbon. But it's the same number. It's a 1-to-1 relationship. Okay, so what that was asking you to do is figure that number out, 0.13 moles of carbon, using a 2 conversion formula. And I want you to get good at writing these formulas, okay? It takes practice, but you can get there. So here we go. We started off with grams of CO2. So let's go back here. We've already done some of these calculations, but we're going to write it out as one big equation. 5.72 grams of CO2. And what we did down here is we converted that into moles of CO2, the 0.13, okay, by using the molar mass conversion. So that's going to be our first conversion here. So it's exactly what we did on the previous page. 1 mole of CO2 over 44.01 grams of CO2. So why are we doing it again? Because we're showing how you can do this all as one equation and not have to do it in little bits and pieces like that. Okay, then the next thing we have, so we cancel grams of CO2, grams of CO2. Now we have moles of CO2, but we need to convert that into moles of carbon. So what's our relationship? Well, we just said what it was. It's 1 mole of carbon for every 1 mole of CO2. So you just write that as a conversion, kind of like what we did in the last lesson. It just looked a little bit different the way we did it. So there's 1 mole of carbon for every 1 mole of CO2. Moles to moles. So moles of CO2 cancels there, and the only thing you have left is moles of carbon. And that's the number we're really interested in. So if we go ahead and compute that, it's 5.72 times 1 divided by 44.01 divided by 1. And if you do that, you'll find that that's going to equal 0.13 moles of carbon. Okay, and that's what we already put up here, is that's how many moles of carbon. So there it says moles of carbon, that's what we have, moles of carbon. The only place this carbon could have come from is here, so that means we can take that 0.13 and bring it over here. That means the subscript to this question mark is going to be that 0.13. I'm not going to try to write it there, it's too small. But that subscript for that carbon is 0.13. Okay? All right, so you may want to stop and think about this a little bit. It's not going to come through just automatically. But if you do a few of these problems, you'll start to see the connection. Okay. Now, let's do the same thing for water, H2O. So, there's just one little twist to water. We had 1.17 grams of water, and we did the conversion to moles down here, and we got 0.65 moles of H2O, okay, using molar mass. So that's 0.065 moles of H2O. The only thing that makes this a little different from carbon dioxide is look at this relationship. For every 1 mole of water, you need 2 hydrogen atoms. Okay, for every 1 bicycle you want to make, you need 2 wheels. So you need twice as many wheels as bicycles. If you want to make 100 bicycles, you need 200 wheels. So that means that however many moles of H2O, and that's how many we have right there, we need twice that many moles of hydrogen. So if I multiply this by 2, okay, I'll just write down what I'm doing. I'm multiplying this by 2. That's going to give me this number up here, which happens to also be 0.13 moles of hydrogen. Okay, and that's really what we're interested in. Since the only place the hydrogen that's in this water, all of the hydrogen that in this reaction went into the water. So this is all the hydrogen there is. And there's only one place it could have come from. It had to come from the hydrogen here in this CH compound. So we're just going to draw an arrow from here to there. And that's going to be 0.13 moles of hydrogen. And that's going to be the subscript for right here, for that H, for that question mark right there. Okay? Now, we haven't yet done the part that it asked you to do. I want you to see if you can write that as a 2 conversion equation. So you're starting with 1.17 grams of water. So writing a 2 conversions equation, compute the number of moles of H from grams of H2O and place in the appropriate boxes. Well, we already did that, so I could show you visually, but now let's write it as an equation. You want to get to where you can write these equations without having to use these graphic organizers and drawing all these pictures. So we start with 1.17 grams of water. Our first conversion is the one we've already done, which is this molar mass conversion down here. 1 mole of H2O for every 18.02 grams. That came from this up here. So let's just write that again. Grams of H2O cancels with grams of H2O. Now we need a relationship. Now we're sitting right here at how many moles of H2O. We need a relationship between moles of H2O and what we really want to know, which is moles of H. As we just said, we have 2 moles of hydrogen for every 1 mole of water, of H2O. 2 moles of H for every 1 mole of H2O. So we write that as our next conversion. Okay, moles of H2O cancels with moles of H2O, and the only thing we have left is moles of hydrogen, which is going to be the unit for our final answer. And so we do the math. 1.17 times 1 times 2 divided by 18.02 divided by 1. And we get 0.1298, but we're going to call it 13. We're going to round it to that. And that's moles of hydrogen. Okay. And that's what we already figured out here visually but that's how you would do it with an equation. Again, you want to get to where you can do these problems just writing these equations without drawing all these pictures like this. This picture is just kind of to help you sort it out while you're new at this. Okay, so it says make a ratio of moles of C and moles of H with the smaller number on the bottom. Well, they're the same. They're 0.13 and 0.13, so it's 0. It doesn't matter which one you consider to be the smaller. Neither one is the smaller. They're both the same. So that equals 1. And for hydrogen, it is the same thing. Okay, so now we have whole numbers there, integers, not these decimal numbers. So I showed you up here, that would be 0.13 and that would be 0.13, but you can't have subscripts that are decimal numbers, so that's why we just did this to get a 1 and a 1. So a 0.13 to 0.13 is a 1-to-1 relationship. It means there's the same number of each. So that means our empirical formula, it says multiply top and bottom of fraction. We don't need to do that. They're both whole numbers, so we don't need to do that step again this time. Let me get back on screen here. This step, we didn't need to do any multiplication because they're both whole numbers already. If that had been a 2.5 and that had been a 1, we'd have to do what we did in the last problem, or a 2.25 or something like that. We don't have to do that. So this is not done. So it's basically very simple. The empirical formula is C1H1. There's the 1 for that. But we don't write it like that. We just write it CH, but that means C1H1. So that's the empirical formula. Good. So now you figured out the empirical formula. Now we're going to take it one more step. We want to know what the actual molecular formula is. It might actually be this, CH. That might actually be the real-world molecular formula. I'm going to tell you right now it's not. There's no such molecule in the real world called CH. So what could this be the empirical formula for? It could be the empirical formula for almost anything, for an infinite number of possibilities. It could be C2H2, because that's a 1-to-1 relationship, so that reduces to CH. It could be C3H3. Again, it's like reducing a fraction. If you have that and you reduce it, it becomes CH. You have the same number of carbon as hydrogen. That's what this is telling you. That's all this is telling you. It's not telling you how many of each you have. It's just telling you you have the same number of carbon as hydrogen. It could be C4H4 and on and on. You get the idea. Okay? So we need to figure out what is this? What is this, the empirical formula? What's the real world molecule? Well, we need one more piece of information. And here it is. To get the molecular formula, that's the formula of the actual molecule that this is the empirical formula for, we need to know the molar mass of the substance. In other words, before we combusted this compound, they weighed it, and they were able to determine the molar mass. How they do that, let's not get into those details right now. It can be done. Even though they don't know what this compound is, they can determine the molar mass. I'll talk to you about how that's done later, but just understand for now it can be done. We can know the molar mass of this, even though we don't know what it is yet. So we're saying that this is the molar mass of this compound, whatever it is. Okay? So it says compute the molar mass of the empirical formula from part H. So this is the molar mass of the actual chemical compound that exists in the real world, whatever it is. We're trying to figure that out. It wants you now to do what's called the empirical molar mass, which is the molar mass of this. So let's go ahead and do that. For CH, it's called the empirical molar mass. You have one carbon, and from the periodic table, that's 12.01. And you have hydrogen, you have one hydrogen, and from the periodic table, that's 1.01. You add those together, you get 13.02 grams per mole. Okay, so this is the actual molar mass of the real compound, and this is the molar mass of this, of CH, of this empirical formula. So now what you do, just follow the instructions. Make a ratio of the molar mass of the molecule, that should be molecular formula, over empirical molar mass, and this is called the factor. It's just a factor, just means a number you're going to multiply something by. So we take this, So let's write out that formula. It's molar mass of the actual compound. Oops, molar mass. Over the empirical molar mass. The molar mass of this, which we just calculated right there, a C and an H. Okay, so what's that's going to be? That's the molar mass. And that's the empirical molar mass. And factor often means it doesn't have any unit of measure. The grams cancels with grams, so that's just going to give us some number. Again, it might not be exactly an integer, but it should be pretty close to one. It will be in the problems that I'm giving you here. Divided by 13.02, and that equals 5.9999, so we're going to call that 6. Okay? So the factor is equal to 6. That's the factor. All right, so let's see. Did I leave you space on the next page to do this? Yeah. Okay. Be sure it gave you a place to do that, otherwise we wouldn't finish the problem. So right here it says the last step, multiply the subscripts by the factor. So the factor was 6. Let me write it out here. And the empirical formula is CH, what we figured out earlier. So it's really, let's write it as C1H1. That's really what it means. So what you're going to do for the actual molecular formula is multiply 1 times 6 and 1 times 6. So the molecular formula, this is your final answer. That's the formula of the actual real-world molecule, which is what we're interested in, is going to be C6, blew it, grand finale, and I messed it up. It's going to be C6H6. So this times this, and this number, that's a 6, times this, C6. So that's your final actual real-world compound that you were able to determine from, first of all, taking how many grams of CO2 and H2O, figuring out how many moles of CO2 and H2O that was, then how many moles of carbon and hydrogen, and realizing that those all had to come from the CH compound. So you figured out the empirical formula, and then by knowing the molar mass, and again, that can be determined even if you don't know the substance, by knowing the actual molar mass, you could then figure out the actual formula for that actual compound, C6H6.